Now we are going to see the second topics for this chapter, which is the error correction. So basically, a semiconductor memory system is subject to errors. It can be classified into two categories, which is the hard failure and soft failure. The hard failure basically is a permanent physical defect, which is the memory cell or cells affected cannot reliably store data but become stuck at 0 or 1 or switch erratically between 0 and 1. So basically, this failure can be caused by harsh environmental abuse, manufacturing defects, and wear. So basically, wear is a damage on solid surface caused by mechanical or chemical. Meanwhile, the soft failure related to the random or non-destructive event that alters the contents of one or more memory cells. Basically, this is not a permanent damage to memory. This failure basically can be caused by power supply problems and alpha particles signal error. Before this, we learned about the two types or two categories of error, which is the hard failure and the soft failure. So basically, both hard and soft errors are clearly undesirable, and most modern main memory systems include logic for both detecting and correcting errors. So basically, this is the error correcting code function. This is the process for error correcting code function. Alright, so we are going to see the process one by one. So the M represents the data bits, K represents the code bits or check bits, while F is the function. So the first thing is the user will or the memory will receive a series of bits or the data in. So remember that our computer only operates the binary bits of data. So there are series of binary bits will be coming into our memory. So this before coming into the memory, so the series of binary bits, okay, will go to the function first, okay, and this function will do certain operations and calculation, and it will produce code bits or check bits. And the data bits and the check bits will be stored inside our memory as a word stored. So our word stored basically consists of the data bits as well as the code bits or the check bits. When the processor wants to fetch back the word stored, okay, so it will produce, the memory will produce again the data bits, okay, the data bits and the check bits, the first check bits stored inside our memory. So this is the first check bits. So the data bits will go to the function again, okay, for certain calculation and operation, and this function will produce the second check bits. So remember that this is the first check bits and this is the second check bits. So the first and second check bits will be compared. Okay, there is a process for comparison for first and second check bits, and if there is an error, okay, if there is an error, these check bits, okay, this word fetch will be sent to the corrector. Okay, will be sent to the corrector, and correction, a necessary correction will be done. And this after correction has been done, the word fetch will be sent out. Okay, if there is a error, okay, if there is an error but correction cannot be done, it will flag an error signal to the CPU. The simplest and the oldest error correcting codes is known as the Hamming code. So basically, the Hamming code is devised by Richard Hamming at Bell Laboratories. So what basically is the Hamming code? Hamming code is an adaptation of the concept of parity, whereby each detection and correction capabilities are increased in proportion to the number of parity bits, or before this we known it as a check bits, added to an information word. Hamming code is used in situations where random errors are likely to occur. With random errors, it is assumed each bit failure has a fixed probability of occurrence. independent of other bit failures. It is common for computer memory to experience such errors. Alright, now we are going to do the Hamming code. So basically, we want to detect a single error and we want to correct a single error with the Hamming code function or algorithm. So remember that we have the M, which represents the data bits, and K represents the code bits or the check bits. So assuming that we have the M, the data bits with 8 bits, which is 00111001. So these 8 bits consist of 8 data. So data 1 basically is the rightmost position. Here data 1 consists of 1 and followed by data 2, 0, data 3, 0, data 4, 1, data 5, 1, data 6, 1, data 7, 0, and data 8, 0. So the data 1 is the rightmost position. The K basically the code bits or the check bits, but we don't know yet what is the check bits. And basically the word is consists of the data bits M and check bits K. Right, so remember the functions, the process of the correcting errors, whereby the data bits will go in and it will go to the function first, and the function will produce a first check bits. Okay, now how we want to find how many check bits inside these 8 bits of data. So the first step, we must find the K or the code bits or the check bits. How many code bits or check bits should be stored in our word? So we need to do a try and error using formula, which is 2 power of K minus 1 equals or bigger than M plus K, the data bits plus the check bits. So we do the try and error. If K is equals to 1, we do the process and we got the answer, which is 1 bigger and equals to 9, which the answer is false. And then we do, if K is equals to 2, we do the process, okay, using this equation, okay, and we got the results 3 greater and equals to 10, which is false. We do again, if K is 3, we do the process and we got the answer, which is 7 greater or equals to 11, which is also false. And we do another trial, which is K, if K is equals to 4. So we do the process, okay, and we got the results which is 15 greater or equals to 12, and this is a true case or true answer. So basically, after we do the try and error process, we found out that number of check bits that should be stored inside our word should have 4 check bits. Alright, now we move to the second step. We have done the first step whereby we try to find how many check bits or the code bits or the parity bits that should be stored inside our word, and we do it using try and error process. Now the second step, we need to find the check bit or parity bit for the word stored. So remember that our word consists of number of data bits plus number of check bits. So we know that our data bits is 8 bits here. So it depends, we can have 8 bits, we can have 4 bits, we can have 12 bits. But for this case, for this calculation or this example, we only use 8 bits of number. Okay, so the data bits is 8 bits. Okay, and we know from the previous step, from the first step, our check bits should consist of 4 bits of data, right? So 8 plus 4 is equals to 12 bits. So inside our word stored, it should consist of 12 bits of data. Okay, and now we must have a table here. Okay, so this table basically consists of the bit position, okay, the check bit, data bit, word stored, and the word fetch. So bit position, basically it depends on how many bits in our word. So it's data bits plus the check bits. We have now here the example, we have 12 bits. So we must have 12 bits of data and check bits. Okay, so we have bit position 1 until 12. Okay, now we want to have our check bit. So how we want to position our check bit? So the location of our check bit is basically at power of 2. So 2 power of 0 is at bit position 1. 2 power of 1 is equals to 2. So this one consists of our check bit 2. So 2 power of 4, okay, so 2 power of 4 is at bit position 4. 2 power of 4 is equals to 4. So it is at the bit position 4. And this bit position 4, we name it as a check bit 4. And then we have another power of 2, which is 2 power of 3 is equals to 8. And this bit position 8 consists of is a location for our check bit 8. Okay, if we have more than 12 bit position, so we can have another power of 2 or 2 power of 4 equals to 16. Okay, if we have more than 12 bits of word. Okay, but now in this example we only have 12 bits only. Okay, so sufficient or enough until 2 power of 3. So our check bit 1 is located at the bit position 1 or 2 power of 0, and our check bit 2 is the location is at bit position 2 or 2 power of 1, and our check bit 4 is at location of bit position 4 or 2 power of 2, and the last check bit or check bit 8 is at bit position 8 or it's equal to 2 power of 3. Okay, so we know that we already know the position for our check bit, which is at the bit position 1, bit position 2, bit position 4, and bit position 8. Alright, so the remaining, okay, which has not determined the check bit yet, it's our data bits. So data bit 1, okay, data bit 1 is located at bit position 3, and then data bit 2 is located at bit position 5, data 3 at bit position 6, and followed by the data bit 4, okay, until data bit 8 at location 12. Okay, so we already know, okay, the check bit position, and we have determined the data bit position. Okay, so we know that our data bits consists of 8 bits, and we can place these bits inside our table. Okay, remember that the data bits 1 is the rightmost position, so data bit 1 is 1, so this one basically inside the data bit 1. And then followed respectively to the other data bits. So here 1 located at data 1, 0 located at data 2, 0 located at data 3, 1 located at data 4, 1 located at data 5, another one located at data 6, 0 located at data 7, and the last bit 0 located at data 8. So this is the second step. Okay, the second step on how we want to find how we want to locate our check bits, how we want to locate the data bits, and how we want to place the bits respectively to the its own table. After first step, we are going to do a second step. Okay, so the first step we do a try and error to find a number of check bits. Okay, so in the second step, we need to find the check bit or parity bit for the word stored. Okay, so remember that inside our word consists of the M plus K. So M is the data bits plus the check bits or the parity bits or the code bits, right? So our data bits, we know our data bits consists of 8 bits, okay, 8 bits of data. So basically it depends. We can have 4 bits of data bits, okay, we can have also 8 bits, we can have 16, we can have 32 and so on, okay. But for this example, we only use 8 bits of data, okay. And our check bits we already found inside our first step, which is 4 bits of data. So 8 plus 4 is equals to 12 bits. Alright, so now we must have a table. Okay, we must have a table, and inside this table must have a bit position. Okay, check bit, data bit, word stored, and the word fetch. Alright, so inside our bit position, okay, it depends on how many bits we have. In this example, we have 12 bits, okay, so we must put the position from 1 until 12, okay, so bit position 1 is always at the right hand side, okay. If we have 8, so this table will be truncated into 8 columns only. If we have 16, we must expand our table and we must have until 16 bit of data, okay. And now we want to find out, or we want to know where's the location of our check bit, okay, where's the location of our check bit. So remember that our check bit must be located, okay, at power of 2. So now we have 2 power of 0, okay, 2 power of 0 is equals to 1. So this bit position 1 must have our check bit 1. We have 2 power of 1 at bit position 2, and this bit position 2 consists of our check bit 2, right? And then followed by 2 power of 2, which is equivalent to 4. Okay, the bit position is 4, and this bit position is our check bit 4. And then we have 2 power of 3, or equivalent to 8. So this bit position 8 is our check bit 8, right? So in this example, we only have 12 bits only, okay, 12 bits only. Let's say if we have 16 bits, we can have 2 power of 4, okay, 2 power of 4. So 2 power of 4 is equivalent to 16. So in bit position 16, we have check bit C16, but in this case we only have 12 bits only, okay, so sufficient until 2 power of 3, okay, to locate our check bit, the check bits inside our data, right? So the remaining bit position which has no check bits is our data bit. So data bit 1 is located at bit position 3, data bit 2 located at bit position 5, data bit 3 located at bit position 6, data bit 4 is located at bit position 7, data bit 5 located at bit position 9, data bit 6 located at bit position 10, data bit 7 located at bit position 11, and the last one, data bit 8 located at bit position 12, right? So now we know the position of our check bit, and we know the position of our data bit, right? So now we can place our 8 bits of data here inside the respective column, okay, respective column. So remember that data bit 1 is the rightmost position. So 1 is located at data 1, okay, data bit 1. So 1 is located here, 0 located at data bit 2, 0 located at data bit 3, 1 located at data bit 4, 1 here located at data bit 1, data bit 5, Another one is located at data bit 6, 0 is located at data bit 7, and the last one data bit 8, which is 0, located at the column for data bit 8. Right, so this is the not finished yet for the second step. Okay, this is the initial step inside our second step, whereby we already added the data bits 8 with the check bits 4. We got 12 bits, and then we must develop a table consists of 12 column, okay, for data bits and check bits, and we know the position for our check bits, we know the position of our data bit, and we must locate the data bits inside the respective column. Alright, so the next one, okay, how we want to find the check bit or parity bit for word start. Alright, so we have the table here. Okay, we have the table here, and the next step, we must find the check bit. How we want to find the check bit, right? So this is the formula, okay, to find the respective check bit. So if you want to find the check bit 1, the formula is D1 exclusive or D2, exclusive or D4, exclusive or D5, and exclusive or D7. For check bit 2, we need to exclusive OR for D1, D3, D4, D6, and D7. For check bit 4, we must exclusive OR for D2, D3, D4, and D8. For check bit 8, we must do the exclusive OR for D5, D6, D7, and D8. After we know that the formula how to find the check bits, we must we must do the operation, the exclusive OR, okay, for the respective check bits. Right, so we know that for check bit 1, we do the exclusive OR for D1, D2, D4, D5, and D7. We must put the respective bits for the related data bits. So data bit 1, okay, if we find in the table data bit 1 is 1, so this one we must locate at this location, okay, and data bit 2 is 0, put it here. D4 is 1, put it here, and D5 is 1, we put inside the respective column, and D7 is 0, so we put it we put 0 in, under the D7, right, and then we do the exclusive OR. So one exclusive OR, so you must remember the rules for the exclusive OR. If both number is similar, both numbers are similar, for example 1, 1, so the results will be 0. Right, similar if the number is 0, 0, so the results will be 0. So in this case, okay, so 1 exclusive OR 0, so this one the results will be 1. So 1 exclusive OR 1, the results will be 0. 0 exclusive OR 1, the results will be 1. And 1 exclusive OR 0, the result will be 1. So you can see that after you do the exclusive OR for these data bits, okay, the check bit, the results for check bit 1 is 1. Okay, so you need to do for the check bit 2. Okay, so check bit 2, you need to do the exclusive OR for 1, 0, 1, 1, 0. So the results will be 1. Okay, and for the check bit 4, you must do the exclusive OR for data bits 0, 0, 1, and 0. So the results will be 1 for check bit 4. And the last check bit 8, you need to do the exclusive OR for data bits 1, 1, 0, and 0. So the results will be 0. So you place the check bit, okay, after you obtain the results for the each check bit, you must place at its designated column. Okay, so check bit 1, the result is 1, so you put it here. Okay, check bit 2, the result is 1, so you put it inside the column check bit 2. Okay, check bit 4, okay, check bit 4, the result is 1, so you put the results under the designated column. And then the check bit 8 is 0, so 0 you put under the check bit 8. So the word start is 1 1 1 1 0 0 1 0 1 1 0 0. Okay, so this is how you want to find the check bit or parity bit, okay, for the word start. And then you combine the check bit and the data bit, and it becomes the word start. You have done two steps in the Hamming code, right? First step and second step. And now we want to look back at the process of the error correcting function. Okay, now remember that you have M, which is the data bits. So you have 8 bits of data, okay, and these 8 bits of data go to the function, okay, to do some calculation and operation. So in here, you know that how many check bits or parity bits or code bits should be added inside the word start, all right? And you also, in the second step, you also done the check bits, how you want to determine the check bits number, okay? So you already know that M is the data bits, 8 bits, and you already know the check bits, 4 bits, and you also know the respective number for each of the check bits, okay? And these, the data bits and the check bits already stored inside the memory and known as the word start. And now we are going to see, okay, if there is any error when the word start wants to be retrieved back by the CPU. Alright, in here, we know that the word start, okay, we have the 8 bits, which is 00111001, okay, and you already put or locate the data bits inside the table, okay, to the respective data bits, and you also found out the respective check bits, okay. So for check bit 1 in the previous steps, check bits 1 is 1, check bit 2 is 1, check bit 4 is 1, and check bit 8 is 0. Okay. So now if the CPU wants to retrieve back the word start, okay, wants to retrieve back the word start, remember that inside the process, okay, when the CPU or the processor wants to retrieve back the word start, it will produce another, which is the data bits, and it will produce the check bits, okay, the first check bits, and the data bits will go again inside the function, okay, will go again inside the function, and second check bits will be produced, and the second and the first and the second check bits will be compared, okay, if there is any error, it will be corrected. All right, so now assuming that we have the word start, we already know the bits, okay, now we assume the word fetch produced by the memory, okay, is 8 bits, 00111101. So this is the word fetch by the CPU and produced by the memory. So this word fetch, the 8 bits will be located inside the table for the respective data bits. So remember, the data bits 1 is the rightmost position. So this one will be put here. 0 is in the data bit 2, 1 data bit 3, 1 data bit 4, 1 data bit 5, 1 data bit 6, 0 data bit 7, and the last one 0 is data bit 8. So you put the word fetch, the 8 bits of the word fetch, into the respective column for the word fetch. And now we want to find out the check bits for the word fetch. The process is similar like the word start, okay, but now we are going to do for the word fetch. This is the third step, okay, inside the Hamming code. So this step, we want to find the check bit or parity bit for the word fetch, okay. So now you already know what is the data bits for the word fetch, and you also know the formula to find the check bits, okay. So you have 4 check bits here: check bit 1, check bit 2, check bit 4, and check bit 8. So the formula for check bit 1, you need to exclusive OR for data bit 1, data bit 2, data bit 4, data bit 5, and data bit 7, right? So you place the respective data bit inside each column, okay. So data bit 1 is 1 for the word fetch. Now we focus only on the word fetch, right? We only focus on the word fetch. Previously, we already done for the word stored. Now we want to do the word fetch, right? So we only focus data bits for the word fetch. So data bit 1, okay, data bit 1 for the word fetch is 1. Data bit 2 for word fetch is 0. Data bit 4 for word fetch is 1. Data bit 5 for word fetch is 1. And data bit 7 for word fetch is 0. So you do the exclusive OR for this check bit, and you get the results, which is 1. Okay, so same for the check bit 2. Data bit 1 is 1. Data bit 3 is 1. Data bit 4 is 1. Data bit 6 is 1. And data bit 7 is 0. Okay, so you put the respective bits inside the data data bits column. Okay, so the results is 0. For check bit 4, after you do the exclusive OR, okay, you got 0. And check bit 8, after you do the exclusive OR, you got 0. So the check bit is 1 0 0 0. So you place back the check bit inside the table. So check bit 1 is 1, check bit 2 is 0, check bit 4 is 0, and check bit 8 is 0. Alright, we look back at the process, okay, the code correcting process. First, we already stored, okay, we know our data bits, 8 bits, and then these 8 bits data bits is went to the function, and inside the function do the calculation and operation, and it produced the check bits, okay, the check bits number. And these data bits and check bits is combined together and become word stored and stored inside our memory. And then the CPU wants to retrieve back the word stored, and the memory produce back again the data bits, okay, and the first check bits, right? And the data bits produced by the memory needs to go to this second function, and inside this function it will do the calculation and operation, and it produce the second check bits inside our word fetch. And we must do the comparison for the first check bit and the second check bit. How the process for the comparison is. Okay, so this is the process, okay, for the comparison. You take the check bit for the word stored and the check bit for the word fetch. So the check bit for the word stored is the first check bit, and the second check bit is the word fetch. So now the check bit for the word stored is 1 1 1 0. So you place the check bit inside the designated check bits, okay, check bits column. And the word fetch, okay, the check bit for the word fetch is 1 0 0 0. So you put 1 0 0 0, okay, inside the respective column for each of the check bit. And now you do the exclusive OR, okay, for the both check bits, okay, check bit 1 and check bit 2. Okay, so remember at the rightmost position is the check bit 1, and the leftmost position is the check bit 8, right? So this one, when you do the exclusive OR, you must remember the rules for the exclusive OR. So 1 exclusive OR 1, it becomes 0, okay. 1 0 exclusive OR 0, it becomes 1. 1 exclusive OR 0, it becomes 1, and 0 exclusive OR 0, it becomes 0, right? So you got 0 after you do the comparison, you got 0110, and these check bits you must change to the decimal numbers, right? So 0110, when you change to decimal number, it becomes 6, right? So you want to detect which position which position contains error. So this one you got decimal number 6, so the error is in bit position 6. So you can see here the bit position 6, okay, which is the data bit 3, okay. For the word stored, basically it's stored bit 0, but when the CPU wants to fetch the word, the bits change to 1. Okay, the bits change to 1, and this is the error, okay, inside the word fetch, and this must do the computer or the processor must do the correction, okay, and using the Hamming code, and it found out that the error is in the bit position 6. Okay, if there is no error, okay, for the word stored and the word fetch, the number should be similar. Data 1 should be 1, data 2 for the word stored is 0, word fetch must be also 0. For data bit 3, suppose word stored is 0, word fetch must be 0 as well. Okay, same to the other data bits. So now you already done the 4th steps for the Hamming code to detect an error. So you already done all the steps in the Hamming code, and you already know which bit position contains error.